One, so we have another AIME problem. So this was number 11. So we have a circle, and then there is a cyclic quadrilateral ABCD, and four sides are given, and we're gonna have some perpendiculars from those ABCDs to the diagonals, and we want to find the perimeter of the quadrilateral that will be formed by those the foot of the perpendicular lines. Okay, so it's not really obvious how things look like or what to use immediately. So which is why we need to start as usual from a figure to see what's going on. So the first things we are told, 4, 5, 6, and 7. So maybe we can just roughly sketch something. So I'm gonna choose AB as a bit smaller, and then BC is slightly bigger than them. Okay, so let's say this is AB. And then BCD will be a bit larger than the previous one. And then the AD should be the largest one. So we have this, this is like 4, this is 5, 6, and 7. And it says right here, A1 and C1 is the feet of the perpendiculars from A to BD. So if you draw a perpendicular from A, so let's label those as well. So the A, B, C, and D. And we want probably our diagonals to see what's going on. So A to BD, if you drop the height from A, so it will be like, based on my drawing, something like this. And from C to BD as well, maybe somewhere right there. So this is A1, and then this is a C1. And if you do the same thing with AC, maybe it's getting complicated already, but I will just make additional figure if needed. So we have A to, like, we're gonna find a altitude from B to AC, because it says B to AC and D to AC. So if I drop the altitude from here, so it looks like somewhere right here. And then from B, so we will get somewhere right there. And this is also a 90 degrees, and then this is 90. So this was 90. This was also as well. Okay, so now we know this is D1. So this is D1, and then this was B1. Okay, so the question is, how do you find the perimeter of those those pieces, like from A1 to B1, B1 to C1, C1 to D1, D1 to A1. So we are going to have a quadrilateral, and we want to find the perimeter of that one. So this is already kind of complicated, which is why I'm going to draw the quadrilateral, maybe just some part of it separately to make it a bit bigger. So which is kind of helpful in general. So, but before I do that, like I see something going on here already. Like if I call this intersection, let's say P, so the angle right here is 90, angle right here is 90. So there's a quadrilateral, which is like opposite angles add up to 180, which is a cyclic quadrilateral anyway. So we can make a circle going through these points. And if you draw this, you can actually do the same thing right here, but it's already complicated looking, so which is why I'll just put it away. So what I will do, I'm gonna draw just the quadrilateral again, slightly bigger, so we can just see things slightly better. So if I have such a thing, okay, so, and in this case, I'm gonna draw only some of these things, but I'm not gonna kind of get rid of this yet because I'll still refer to that diagram. So, and then this is our pieces. So this is B, A, C, and D. Okay, so now we need to remember our perpendiculars probably. If I drop my perpendiculars, some of them. So if I draw the one from D to AC, I'm gonna, even though this is kind of better, but I'm gonna make it slightly closer to C so we can have a bit bigger figure. And the same thing from C to BD. So let's say this is my perpendicular. So as long as you know what you are dealing with, so we can play with our diagram to make things a bit easier to see. So which I'm trying to do now. And if I do the same thing with this one, so I'll go with that. So that's A to BD, and so we should have another one, something like this. So this is 90 and this is 90. And then this was B1. Then this is A1, and then this is D1, and then C1. So you may connect those just to see. Let's go ahead and do that, because that's also one of the things that we are gonna need to do that, because I mean one of the things that actually give us a hint, because that's what we are trying to add it together, right? And then that is not easier to see, but what we already have is like 4, 5, 6, and 7, but we need to relate those somehow to the smaller one. You know, one of the things that I immediately remember, like when you see like cyclic quadrilateral, right? The Ptolemy's theorem. So if you don't remember, so I will just leave some recording in the description. You can review that. And the Ptolemy was telling us that when you multiply the opposite sides, which is 4 and 6, and then plus a 5 and 7, this is add up to equal to product of the diagonals, which is AC times BD. So right now, I'm not sure if this is going to be too helpful, but it is something we always use. So which is why I'll just put it there anyway. The next thing is, you know, we just said right here that was a cyclic quadrilateral. So which is why I'll just name this as P as before. So, you know, there is the angle at this point P. So one of them is like acute, the other angle is like obtuse, which we do not know yet. But I'm gonna call this is alpha. So if this is my angle alpha, maybe I should use different. So let's say this is alpha. And like whenever you look at this 90, so the like D1C, and then we had the same story right here. So C1D. So these two 90s are facing towards DC, which is another place that we can draw a circle, because that will make our diameter. So if you kind of don't know why, so it's just one of the fundamental features of the cyclic quadrilateral. So I'm going to leave for you to explore. So if you draw that, so you will get a nice circle without, even though mine doesn't look like, but at least you accept that, right? So you got a circle right here. Why this is important? Because we have the angle right here. So I'll just say this part, not the entire 90, but the angle B1, D1, C1. So this angle, whatever angle right here, okay? So that complementary angle was the other part right here. That is actually supplementary of this angle is gonna be this one, like C1 D1C. So this angle and this angle add up 180. But at the same time, this angle right here and the angle right here is also supplementary, because those are the two angles opposites on the quadrilateral. So which is why those are also add up 180. Since this is supplementing this angle, and then this angle will supplement this one, so the angle right here has to be same as the angle like PD1C1. So let's remember that. So P D1C1 is congruent to the C1DC, or just CD C1. So, and then that will make things a bit better, because the triangle PCD1, this triangle, and PDC, has already two angles that is congruent. So the P is the same as P, and then this angle same as this one. So the third angle has to be same as C. So we can write the ratios. Okay, they are similar. So the first thing is the side opposite to this, the alpha, which is C1 D1 over the same angle opposite to CD in the larger one. So that's equal to that. And from P to D1, which is the third angle, and the third angle is right here opposite to PD, which is divided by PD. And similarly, the P to C1, the third side, and is equal to, corresponds to PC, so that's divided by PC. And these are all equal because of the similarity, but also, if you look at the triangle, let me highlight that slightly differently. If you look at the triangle PD1, D, like if you look at this triangle, D to this segment was perpendicular, so this entire thing is 90 degrees, and then alpha is one of the acute angles in a triangle. So which is why if you wanna look at the ratio P to D1 divided by PD, which is like one leg of the right triangle divided by hypotenuse, and the leg is the one that is next to this alpha. This ratio is the same as cosine alpha, which is actually nice to see because we are going to use in the next step. So, and then if I see that P, D1 C1, so D1 C1 divided by C is equal to this. So if I can write this guy C1 D1 alone, so that will be written CD times cosine alpha. But I know CD was 6, which means I know C1 D1 6 times cosine alpha. And if I can write the every sides of that new quadrilateral in terms of those A, B, C, D, then I can just write the entire perimeter in terms of just cosine alpha. And then the next question would be, how do I find the area cosine alpha after, right? So which I'll try next. So another thing, by using similar reasoning, we have the same thing story right here on this side, because this angle is also 90 degrees, and then this angle is 90. So that this 90 is facing towards AB. So which means we have another absolute parallel going through AB1, A1B. So something like this. And the same story is kind of this part. So that triangle and the larger one is similar because of the supplementing angles as the reasoning right here, the same on this side as well. So if I go with the ratio now, A1, B1 over AB equals PA1. So this is P, A1 is right here, or is this one. So the PA1 over, not PB, it has to be PA. So because angles on the other side, other corresponding part. So the divided by PA. And if you are not convinced with this, do the same thing I did in this ratio to get the second one. So then it will be equals PB1 over PB. And that same things this is also alpha. So if you write the cosine, these guys will be all equal to this. This is promising because if I want to write now the sum of those four segments, so here's what we are gonna get, A1 B1 plus A1 D1 plus D1 C1 C1 B1. So if I take the first equation C1, first ratio with this, if I multiply both sides by CD, and then CD is 6 cosine will be C1 B1. So this is going to be 6 times cosine alpha. And the same thing with A1 B1. So that's going to be AB times cosine. AB is 4. So that should be 4 times cosine alpha. And the question is now, we got the two sides because we have the similar triangles, but how can we get the other two? We can kind of guess something, but if you actually have time, if you can prove it, just go for it. but on the test, maybe you can guess the same reasoning should work. But the thing is, there's no cyclic quadrilateral on these two sides, so which is the problem. But the good news is, when you look at the ratios, a bit carefully, like we have P to B1, you know, in this case, for example, PB1 divided by PB. So like, look at this, PB1, so maybe I should highlight a bit. So this guy to this guy, okay, is cosine alpha, and PC1, if you look at this one, PC1 divided by PC, so PC1 divided by PC. So the ratio of this to that, ratio of this to that is equal. So if you look at it, PB1C1, this triangle, and P, B and C, that triangle has two sides are proportional, and the angle in between this one and this side, like those two proportional sides are congruent because they are like vertical angles, which will make those two triangles are similar. And since we kind of said right here, let me write that a bit clearly. So the P B1C1 is similar to P. So I said B1, so that was, I guess, this one BC. So BC by the side angle side, right? So they are similar by side angle side. So then the ratio of the third side, which is B1 to C1 divided by B over C, has to be same. So B1 C1 over BC has to be that ratio, but we know that ratio, PB1 over PB, was cosine, so we can just say that's equal to cosine. And if I use the same reasoning with the other part, that will be equal to like A1 to D1 equals A to D as well, which will be kind of similar reason as this guy, but I'm not going to write again. So that is equal to A1 D1 over AD. And then that is also cosine alpha. So now we can replace those. B to C is divided by BC, and then BC was like 5, so that should mean this guy will be 5 cosine alpha, and then this would be 7 cosine alpha. So if you add those together, so you get 22 cosine alpha. And the question is, this is what we are interested. Only thing is we need to know the cosine alpha, which we do not know yet. Okay, but let me clear these a bit because I don't think we need these anymore. So as soon as we get the cosine alpha somehow, then we are done. So one of the things that we probably can use is our like sine formula, because sometimes area of a figure can be done a couple of ways, and if we can try that, that will help. So this was the one information we kind of put it right there, but we never use it. But at the same time, if I can find the area of this entire ABCD in two different ways, that will make useful. So the one way is using a sine formula. You know, if you know the area formula for a triangle, it's just 1 times A times B times sine, and measure out the angle in between two sides. But if I take this triangle and this triangle, and add them together, we actually can apply this in the quadrilateral, which is going to be, you can prove as well, is equal to area of the quadrilateral. I'll just say ABCD. By making this general, is going to be 1/2 times AC times BD is going to be the area. And I do know AC times BD, which will make areas like known. So now if I can find another expression in terms of the area, then I'll get something useful because I know the area already with this. Okay, so another way to look at the area of the quadrilateral, it's kind of using similar expression for the Heron's formula. So if you know, when you know the three sides of a triangle, you can use the Heron's approach to get the area. And like with the similar reasoning, we have another formula for the quadrilateral, and it's called Brahmagupta's like formula. So we can use that, which is kind of similar to the Heron's approach. We just take the S, which is 1/2 of the sides, which is like 1/4 5, 6, 7 divided by 2, which is 11. But the area is going to be not divided by 2 because this is not a triangle. So area is just going to be this number minus each side. And we multiply those. Okay, so if I do this, like this is going to be 7, 6, 5, and 4. So I think that's the only perfect square. We can pull outside. So that should be 2 root 210. Okay, this is the area. We know the area can be done like with this as well, which is I should multiply sine alpha. So this is the area as well. So if I make them equal to each other, so which will give us the 2 root 210 is equal to 1/2 times 59, I guess, because that's 24 and 35, and then times sine alpha. So this is good because if I know the sine, I need to find the cosine, and when I have the cosine, we are done. So I can just say this is 4 times 2 root 10 over 59 equals sine alpha. So now we can just kind of go ahead and use the I don't know, right triangle and find the cosine value, which I'm gonna leave you to try that part, but I'm gonna kind of guide you at least. So let's say this is alpha, and then sine value will be 4 root 210 over 59. You can use the Pythagorean to get this one. If you do so, you will get 11, which is good. And from there, so you can get cosine alpha is equal to 11 over 59. So if you don't want to use, you can use Pythagorean identity as well to get the cosine, but same thing basically with that. So our final answer should be like 22 times 11 over 59, which is going to be 242 over 59. So we are looking for the sum of those two numbers, which is going to be 301. So it took a bit longer, but we kind of use a lot of things in one problem. The cyclic quadrilateral is really big deal, especially with AMC 12 and AIME. So this was another one. And we need to remember the Ptolemy's for sure as our one of the foundation, as well as Brahmagupta's like approach as well, which is not too fancy as you see. And otherwise, the question wasn't really that much a deal, but seeing things are not that simple. But that was number 11. So I hope that was clear. I'll see you next week.